Well, how's everybody doing out there? Well, welcome to day 23 of Corona Online School. So, today we're actually moving on to hypothesis testing with two variables. So, we're going to go through kind of the same steps that we did for one variable. So, we're going to look at when sigma is known, but in this case, we'll have two different sigmas because we're going to have two separate means that we're trying to work with. Then we're going to work with two means when sigma is unknown, which is going to be the more realistic case. And then when we're trying to calculate or hypothesis test two proportions in this case. So again, all this is going to look very similar. So one of the reasons I wanted to spend a lot of time in chapter 9 and make sure everybody seemed to have chapter 9 down is because honestly, if you can get that, this is going to be pretty much exactly the same. So setup's exactly the same. The calculations or finding the p-value can be a little bit trickier in the sigma unknown case, and we'll see why because some of the formulas are a little bit more complicated, but it's not so bad for the sigma known and the probability one or proportion one. So again, even though it's two variables, our claims are still going to be exactly the same, so it's going to be a four-step process just like we had before. And so again, if we look at our state the hypotheses, so notice in this case, instead of having mu1 equal to some number, mu1 is always going to be related to the mu2 in this case. But otherwise, everything else lines up the same. So our equals go with our not equals. Our less than or equals goes with our greater than. Our greater than or equal goes with our less than. So in some ways, this is actually maybe even a little bit easier to set up because it's always going to be mu1 and mu2. It's just a matter of making sure you get the inequality right. We don't have to figure out, well, what's the other number and stuff like that, which is kind of nice. All right, so our test statistic is a little bit more complicated in this case just because we've got two different means that are actually going on in this situation. So notice our test statistic to find our z-score, instead of just being like x minus mu divided by the standard deviation squared, in this case, we've got to take the differences of the sample means, which is that, minus the difference of the population means, and then all divided by this square root of the standard deviation squared added together. So again, it's a little bit trickier to calculate the test statistic, but it's not terrible. So we can do it. And then finally, calculating the p-value is going to be pretty much the same. Now in this case, notice we're only using the z-score form, and that would be true because we can't really use the way I did with the mean and the standard deviation because we've got the two different means in standard deviation. So the only way to do this using normal CDF is by actually using the standard normal in this case. So 0 for the mean and 1 for the standard deviation. We can't use the actual data values themselves. And then our draw a conclusion is going to be exactly the same. If p is less than alpha, we reject h naught. If p is greater than alpha, we fail to reject h naught. And there is a calculator command where we can actually do the full-blown hypothesis test on. And in this case, for the sigmas known, it's going to be the two-sample z-test. So instead of having just plain old z-test, which is what we would have used for one variable, we want to use two-sample z-test because we've got two variables in this case. And so again, it works just like it did for z-test. You can enter just the data value. You can enter the data value. So if you have just a list of data with no means and standard deviations, you can enter it that way. Or if you have the actual mean and standard deviation, you can just plug those in and stuff like that. And then again, when you hit calculate, it'll give you the p-value. It'll also give you the z-score and stuff like that. And then this one has a draw command where you can actually see kind of what it would look like on the normal curve. So let's dive in and look at an example here. Let's see how we can actually do this. And I'll show you how to use how I would do it by hand, like what I call by hand predicting the method, and then how we'll do it using that calculator also. So I'll show you both. And then there's one of these guys for you to practice, and then we'll move on to the next type. All right, so the mean RPMs of two competing engines are to be compared. 10 engines of each type are randomly assigned to be tested. Both populations have normal distributions, and the following table summarizes the details in this case. So we've got engine 1 had a sample mean of 1,500 revolutions per minute with a population standard deviation of 80. Engine 2 had a sample mean of 1,600 with a population standard deviation of 90. Does the data indicate that engine 2 has a higher RPM than engine 1? Test at the 5% level of significance. So again, before I actually write down what the hypotheses are, I like to kind of write down any information that I have. So in this case, my sample, whoops, got the wrong pen here. So my sample mean for X1 is going to be the engine 1, so that's going to be 1,500. Its population standard deviation we saw was 80. So here's my sigma of 1 is 80. And my N of 1 is 10. So notice in both cases, 10 engines of each type were randomly selected or assigned. So in this case, N1 and N2 are both going to be 10. So now let's write down our sample mean for engine 2. So in this case, it was 1,600. Our standard deviation for engine 2 was 90. And again, N2 was also 10. So eventually we'll need all that stuff. So now it's time to write down our hypotheses. So in this case, does engine 2 have a higher RPM than engine 1? So what this is saying is, does engine 2 greater than engine 1? But we want to think of this in terms of mu. So in this case, I usually like to have the mu1 on the left. So I'm going to kind of rewrite this so it looks like engine 1 is less than engine 2, which means I'm going to get mu1 is less than mu2. And so that means my H1 has to be the greater than or equal to mu2. So if you wrote it as mu2 is greater than mu1, that's fine. Like, these are interchangeable. Just for me, I typically like to always have the mu1 on the left, and you'll see why, because that's kind of the way the calculator writes it as well. So, but if you wrote mu2 is greater than mu1, it's right. There's nothing wrong with that. But all right, so let's take a look here and calculate our test statistic for this guy. Oh, and I forgot to write down our alpha level. So our alpha level is 0.05 in this case. All right, so our test statistic, so again, this is finding the z-score, but this z-score is a lot trickier than, or looking, at least, than the other one. So again, what we're going to get is, the x1 minus x2 minus, let me make sure I get it written down here right, so mu1 minus mu2, all divided by the square root of sigma 1 squared over n1 plus sigma 2 squared, over n2. So I think I got that all right. Yep, perfect. All right, so now let's just plug everything in. So in this case, our sample mean for engine 1 was 1,500 minus x2, x1, which is 1,600. And then all divided by our 80 squared over 10 plus our 90 squared over 10. And now in this case, notice we don't actually know what the mu1s and the mu2s are or anything like that. So in this case, we're kind of treating them as they cancel out. And so we're really just going to have x1 minus x2 as our top number, and then these standard deviations down at the very bottom in this case. So what we get is, on the top, we get negative 100. And then on the bottom, let me type this into the calculator here real quick so we can see what it looks like. All right, so if we do this in one step, we're going to want to type this as parentheses or square root parentheses, and then 80 squared. Oops, hit the wrong thing. So 80 squared divided by, oops, oh my goodness, I'm messing this up. So 80 squared, come out of the exponent, divided by 10 plus 90 squared, come out of the exponent, divided by 10, and then in parentheses. So that looks like it gives us 38.07. Well, I'm going to leave that as my answer for right now. So that way I don't have to round. And then my top number I think was 100. So if I do 100 divided by, and then hit second enter, or second negative sign, that'll pull up that previous answer. And so that way I don't have to worry about rounding anything in this case. So it looks like my z-score is going to be 2.63 in this case. So let's write 2.63 for our z-score. Oh, I think it was negative 2.63, sorry. And this was 38 point something, something, something. So, all right, so this is our z-score. So remember me, I like to use my, I like to kind of go in figuring out whether this is going to be a fail to reject or a reject just by sort of looking at the z-score and comparing it to the alpha level right away. So remember, with an alpha level of 0.05, we can use inverse norm to figure out what that z-score would actually be. So in this case, since we're trying to prove the bottom half, then what this is saying that there's going to be 5% in the blue area, which is going to be our reject H naught area. And that means that there's going to be 95% in the fail to reject H naught area. So I've already done the work for you and did inverse norm to get that negative 1.645. But if you forget how to do it, I can show you real quick. So if we go to Graph and Calc and go to second vars and then inverse norm. So again, what we're trying to do is we're trying to calculate that bottom 5%. So we're doing 0.05. And then we want to do the standard normal curve in this case. So 0, 1. And so that's where our negative 1.65 comes in. So what that's telling us graphically is that, that basically negative 1.645 is the kind of the first value to as we go from, say, right to left, that's going to be in the bad zone. So any number z-score smaller than that is going to be in that blue region, and that means we're going to reject H naught. So knowing that we've got negative 2.63, that tells us that that's going to be somewhere over in this area. So that means that clearly the z-score is inside the blue area. So our gut feeling should be this is going to be a reject H naught. And really we could kind of say it is because, unless we screwed up the z-score, which would be the only thing. So that's why it's good to do a couple different ways, to check it a couple different ways. So based on what I've seen with my z-score, I think it should be a reject H naught. But now let's verify and use our normal CDF to check it also. So in this case, we'll do normal CDF. So since this is the lower bound, we want to do negative 100,000. And so we want to do our negative 2.63 as our upper bound. And then again, so this one we're using the standard normal, so we want to put 0 and 1 in there. And so now we want to see what our p-value is and see if it's less than 0.05. So let's go back to the calculator. So second vars, normal CDF, negative 100,000, comma, negative 2.63. Comma 0, comma 1. So it gives us 0.004. So let's go back and write that down. So our p-value is 0.004. So in this case, how does that relate to alpha? So in this case, that's less than 0.05. So that means this is good. So this means that it's going to be a reject H naught. So that's why now we have two confirmations because we've got our z-score in the blue area, which means that it's a reject. And now we've also shown that our p-value is less than alpha. So with both of those, it definitely means we've done everything right. So our conclusion would be, since our p-value, whoops, since our p-value is less than alpha, we reject H naught. Which means that in this case, that means our mu1 is mu2 is true. So that means that engine 2 does have a higher RPM than engine 1. So that means that engine 2 than engine 1. All right. So is that okay? So again, we can do these just like we did all the other ones. I mean, it's a little bit messier trying to find the test statistic, but other than that, we're still doing the normal CDF. We're still trying to figure out where the test statistic would live on the normal curve and all that kind of stuff. So now let's go back and check a third way. So let's use that two sample z-test and see if we can get it right that way as well. All right, so let's flip to the calculator real quick. So this is going to fall under stats and then under calc, and so under test, sorry. And so the third one on our list is the two sample z-test. And so again, we want to type in all the different information that's given. So our sigma 1, I think, was 80 if I remember correctly. My sigma 2 was 90. My X1 was 1500, I think. My N1 was 10. My X2 was 1600. And my N2 was 10. And then notice right away we've got our test statistic is negative 2.63. So that means we did a really good job finding our test statistic. So that's good. Now our p-value, be careful because we're on the mu1 not equal to mu2. So that's not the one that we want. We want the one mu1 less than mu2. So we want to click that button. And so in this case, we get a p-value of negative or 0.004, which I think is the same p-value we had before. We can see our little shaded in region of where, now the shaded region they're showing us is actually where the test statistic, where the z-score is falling, as opposed to what I do with the alpha score. Like if we were doing our alpha score, it would look, well, you can't see where I'm pointing, but it would be like somewhere around negative 1.6, because I like to show how the test score actually lands in the alpha. So all they're showing is just the z-score graph, but it's still to the left of our alpha, which is perfect. All right, so that works. We did everything good on that one. So with this in mind, go ahead, stop this video. I'm going to make another video for the next section. So in this case, since we're not going to do many that fall into this type, I only have one practice problem for you guys to work on. So do exactly the same thing I did above, state the hypotheses, calculate the test statistic. I didn't draw the alpha on here, so I would recommend you find the alpha and draw it in, and then see if your z-score lands in that same little shaded region. Use normal CDF to calculate the p-value, draw your conclusion, and then as a check, go back and try the two sample t-test to see if you come up with the exact same answer and stuff like that. So at this point, stop the video, practice that, and then when you're done, come on back and we'll look at 10.2, which is when the sigmas are unknown. So good luck.